Hello everyone and welcome back to L582, Modeling and Control of Electric Machines and Drives. During the past two lectures we were talking about the speed control of three-phase induction motors, and we just found out that the most attractive method to do the speed control of the induction motor is using the V/F speed control by controlling the frequency of the voltage applied to the stator, and this controls your synchronous speed and in turn controls your mechanical speed. And we figured out that we need also to control the voltage while controlling the frequency to keep the V/F ratio at the rated value, and this keeps your magnetic field at its rated value, not sacrificing or not just making it very high to go into saturation or very low, and this reduces your torque capability. Okay, so the last lecture we started talking about how actually you can implement this. So we just found out the theory of all that, but how actually you can control, or how you can control the frequency and the voltage going to the machine. Like we just gave them a name last time, the VSDs, or sometimes we call it the VFDs, okay, which is variable speed, that is for S, or variable frequency, that is for F, drives, okay? And that's how it can actually you can control the frequency and voltage of the three-phase induction motor, and this using power electronic converters like we said last time, okay? So let me grab you this schematic diagram of this kind of variable speed drives, and this should look like that if you want to look at it at any kind of a textbook or something. Okay, so yeah, okay, move it down a little bit like that, fine. So that is your motor, so that is your three-phase induction motor, okay guys? And this is, if you just remember last time, that is the first power electronic converter we're using, which is three-phase rectifier. It's like you've seen here, 6 diodes used to rectify the voltage. So actually the input here is the grid voltage, okay, which is three-phase AC voltage but with fixed voltage and fixed frequency, okay? That is the voltage you can find from the grid. It's three-phase AC voltage with fixed voltage and fixed frequency, yep. So we applied from here to this 6 diodes, which is diode bridge, three-phase rectifier. This rectifies this and turn it into a DC voltage, okay? Over here, which this guy is a capacitor, we call it the DC link, okay? This capacitor is used to smooth the output of the rectifier to make it like pure DC voltage as much as possible, okay? So here you have a DC voltage. Now that's the DC voltage, that's positive, negative DC voltage, okay? We call this VDC, okay? And this DC voltage is going to the other stage, the other power electronic switch here. Those 6 power electronic switching devices, or 6 power electronic switches. It can be MOSFETs, IGBTs, or other kind of switches, okay? And this guy, those 6 are just also three-phase, but we call it inverter, okay? And this guy actually just transforms the DC voltage to AC voltage again. So it takes this DC voltage from here and transform it to an AC voltage. So it goes here to the motor. It's also again three-phase AC voltage, but now it is controlled voltage and controlled frequency, okay? So at the beginning we had three-phase AC voltage but fixed voltage and frequency, and now we have also three-phase AC voltage but with controlled frequency and voltage, and that's all we need to do. It can just control the frequency and voltage that is applied to the terminals of our three-phase induction motor, okay guys? How this control of the frequency and the voltage happening? Okay, so the control of frequency and voltage output of the inverter happens by controlling the pulses which operate the switches. Okay, so this inverter has 6 switches, and those switches can open and close by applying pulses to them, as you already had in your power electronics and electronics courses. Okay, so if you can control the frequency and the voltage, or just the rate of these pulses go into these switches, you can actually control the frequency and voltage out of this inverter, and by means this control the frequency and voltage of your motor. Okay, guys, we're not going so much deep in this because that's basically belongs more to power electronics courses rather than to be in machines courses, but I'm gonna just give you a glimpse of the maybe the most famous method of controlling these switches, okay, which is the sinusoidal pulse width modulation. Okay, the SPWM. It's a method of how you can actually generate the pulses that go into these switches of the inverter, so you can control its output in terms of frequency and voltage. Okay, how this happened, let me again have you look with me at a schematic that's just illustrate this. Okay, so here is what's really happening. Okay, guys. Okay, we call it sinusoidal pulse width modulation because actually it uses a sinusoidal signal as your control signal. Okay, where this, let's see. First of all, this is in the control pattern, all that. So this happens inside your controller. Okay, so you have something to generate these pulses for you, and maybe a microcontroller, an Arduino, a computer connected to a DSpace, or any other kind of controllers you can use. Okay, so this happens inside your controller. Most of the time it's just done by software, so you just program those stuff to generate those pulses for you, and then you have some sort of interface that convert this from being just a code pulses into real pulses go into the switches. Okay, again, we're not going so much in details, it's out of our scope, but we need to understand the main idea of how this happens. Okay, so inside your software or inside your control scheme you're just having, you need to have 2 kind of signals. This triangle signal, the red one you're seeing here, we call it the carrier signal. It can be a triangular signal like this, or sawtooth, something like that. Okay, guys? And there's another kind of signals, those black and blue ones. This, we call them the control signals. Okay, guys? And like you see in here, those control signals are sinusoidal. That's why we call this guy a sinusoidal pulse width modulation. Okay, guys? So what will happen is, by controlling the frequency and magnitude of this control signals, we can actually control the frequency and magnitude of the voltage output. Okay, what will happen is you just find or just determine the frequency and magnitude of the sinusoidal wave you want, and then it's compared with the carrier signal to produce your switches, your pulses that go into the switch. That's basically all happen. Okay, so what happens here is the control signal, which is you determine its magnitude and frequency, okay, is compared to a carrier signal with fixed magnitude and frequency. So you set them to a proper number by experience and just leave it without changing. Okay, this comparison gives you the pulses to operate the inverter switches to generate voltage at required magnitude and frequency. Okay, that's really the case. So let's take an example. Look with me at this blue signal. That is the control signal here. By the way, because we're talking about three-phase inverter, you should be having three-phase signals. Okay, so you don't have just one sinusoidal signal, you have three-phase signals and shifted by 120 degrees. So you see, for example, it's just giving you two signals of them, but you need a third one, also phase shifted by 120 degrees. Okay, guys? So that's the whole point. So look at the blue phase with me. What happens is, with the instance that this blue signal is higher than the carrier signal, which is the red one here, for this period maybe, here this is higher than it. So that will happen actually here. Okay, so look at the blue one down, just go down here. Okay, whatever this control signal is higher than the carrier signal, you have a pulse on. Okay, see pulse on, so that means the switch is on for now. Okay, guys? On the other way, look at this period maybe. This period is now your control signal, which is a blue one, is less than the red one in magnitude. And that is, if you just go down here, you'll see it like here, which is off. There is no pulse. The voltage that's out is just out. That is off. See what I mean? That is the whole point of just you compare the sinusoidal signal to the carrier signal, and this comparison gives you the pulses that's going out. Okay? So you do this with the three signals. So the black signal here just gives you this pattern, the black ones, and the blue ones here for the other signal that's shifted 120 degrees give you this. So that is, for example, is phase A, and that is, for example, is phase B. Okay, guys? What really happened if you want a line-to-line voltage, which is basically VA minus VB, that is giving you the line-to-line voltage, VAB. Okay? Look here at the line-to-line voltage, which is the green here. So if you just subtract those voltages, this one, those pulses, which is giving you phase A, and those voltages giving you phase B, this subtraction, which is giving you the line-to-line voltage here, will look like this green signal. If you look at this green signal, it will look so much like a sinusoidal voltage. Okay, guys? And that's what I'm saying. Using this, you can generate an AC voltage out of a DC voltage. Okay, guys? That is the whole point of that. So you have these pulses, and now you have the AC voltage outside. So it's not pure sinusoidal like you see, it's some sort of pulses like that. And it's typical, so you don't get a very pure sinusoidal wave. You have harmonics inside them, and that's why we use filters to filter out as much as we can from these harmonics to get as close to sinusoidal voltages. So again, refer back to your circuits courses when you just had some time to go with filters. So you use filters after this circuit most of the time to filter out most of the harmonics and get close to the sinusoidal voltage as you can. So actually that's a problem actually using those power electronics, because power electronics all the time generates more harmonics in the system, and these harmonics are not good. That means your waveforms are not pure sinusoidal, but rather it just looks like you've seen here, which is basically not very sinusoidal. But like I said, you can use filter to filter as much harmonics as you can. You will not be able to filter all the harmonics, still will be some harmonic content, and this is not good for the devices, all that stuff, but it is the magical word to have all the time that nothing comes without a cost. Okay, so it is the method, or the most actually widely used method to control the three-phase induction motor speed, and you have to deal with this harmonic content. Actually, we try to, like I said, use filters to reduce it as much as we can, but anyways, it's inevitable in our power systems today while we use so much power electronic converters. So we had some sort of what we call now in the literature like the harmonic pollution inside our power system. But again, as I said, with the widespread of using power electronics control over the power system devices, which is actually give us so much advances in the control and even the protection schemes with our power system devices. So actually, yeah, we can pay the price of just dealing with the harmonics, because actually we get so much benefit by using the controlled power electronic converters into our power system devices, including the machines like we said here. Okay guys, so actually there is other different ways of generating the pulses, not just this sinusoidal pulse width modulation, but I've just given you an example. And actually sinusoidal pulse width modulation may be one of the most famously or widely used methods. There is other means, but like I said, it's out of our scope for now. We mainly want you to understand the basic idea of controlling the three-phase induction motor without going much in details into this. Like I said, it is mostly belong to other courses rather than the machines modeling courses, okay? But I hope you just get the basic idea of actually how we do this, okay? So this happens inside the controller, and these pulses are just goes to derive your actual switches here. You seen those switches, those pulses go into derive these switches in the actual circuit you're seeing here, and this actually controls the voltage and frequency of the three-phase induction motor at reality. Okay guys, okay, so here's what happens actually again inside the controller. Okay, so let me call this the control scheme. Okay, so inside your controller, what you do is you have here a frequency command. That means you are inputting the frequency you want the machine to work at. Okay, and here is the switching pattern, call it maker. Okay, for example, that is the sinusoidal pulse width modulation we have just discussed over here. Okay guys, so you're just inputting the frequency command here, the frequency you want the machine to work at. Okay, and from this frequency command you will, or just your program or just your software should multiply this by the ratio V over F rated you want to generate your voltage command. Okay, so this is your voltage command. Okay, so whatever the frequency you want the machine to work at, you should multiply by the ratio V over F rated, which is for our small machines here should be 208 volts over 60 hertz, which is the rated voltage and frequency of the motor, and this will get you how much volt according to this that should be going to the motor. Okay, and like we said on the last lecture, if you were just dealing with a very small frequencies, you should be adding some sort of a boosting voltage, if you remember. Okay, it depends, and this will get you here the voltage command. Okay, the actual voltage command, if you will add the V post or not, depending on you're just having a small speed or not. Okay, so those two goes inside here for your software, just the piece of code that generates your pulses using the sinusoidal pulse width modulation like we just illustrated. Okay, so you're here, you're having your voltage command and frequency command. Like we said, this voltage and frequency command controls the voltage and frequency of those carrier signals, which is the black blue one, and there's another third one also for 3 phases. Okay guys, and this will create the pulses that's going to the inverter switches. Okay, that's how actually this is done. So what you do is you input your frequency and that's it, and you should be calculating the voltage out of it by multiplying by V over F rated, or if your frequency of over the rated frequency, the voltage will be just freezed at the rated voltage like we said last time, and then you get your voltage command and frequency command go into the sinusoidal pulse width simulation to generate the pulses that go to the inverter switches and give you the frequency and voltage you want. Okay, guys? The whole point is you're just inputting the frequency, and this is controlling your synchronous speed, 120 F over P. Okay? But what about your mechanical speed, which is you basically need to control? We're not trying to control the synchronous speed, we're trying to control the mechanical speed. Okay? So like we know, the mechanical speed equals 1 minus S times NS. Okay, guys? So still, you're controlling the synchronous speed, but there's the slip, and the slip depends on load. Okay? So it depends on the load also. So if the load changes or the load goes up, the slip will go as up with it, and then your mechanical speed will keep going down. Okay, guys? So yeah, you're getting close to the mechanical speed you want, but if the load changes, the mechanical speed will change also. So you need to just manually readjust it again and again. Okay? And that's why we call this open loop control. Why? Because there is no sort of a feedback here that is actually telling you that the system has been changes in its state and you need to recalculate it. That's why if you want your speed to be strictly at some value and does not change, we need to go with what we call closed loop control scheme. You should have been this between you just have in your back control courses. So the whole point is that is our three-phase induction motor, yes, and this is your controller, okay, and this given your pulses out of the controller to actually here, the power electronic switches. Okay, so that's your controller, and that is your power electronics. Okay, so the controller just gives the pulses to the switches, and the power electronic switches gives the voltage and frequency to the three-phase induction motor to work with it. The whole point is, for this closed loop scheme, we use a speed sensor here. A sensor senses your speed, and then it gives you what we call a feedback. Okay, this feedback goes here to be compared with your now speed command. Okay, and the difference between them goes to your controller. Like this, what happens actually is whatever the load changes, the speed changes with it, but because you're measuring the speed and feedbacking this actual speed to your controller, what will happen is your controller will make sure actually to track this change and keep updating the voltage and frequency going to the machine to keep your speed fixed at your command speed. Okay, guys? So it's more complicated scheme as we need, and it requires a speed sensor that senses your speed and all that stuff, but you use this if you need your speed to be fixed at whatever speed you want to be. Here you're directly controlling the mechanical speed, but in the open loop here we're just controlling the frequency, and this controls the synchronous speed. And you know, the slip is changing by the load, and this will change the mechanical speed even if you are fixing your frequency command. You know what I mean? So if you want more precise control, you go with the closed loop. As you know, everything comes with a cost. There's a more money here you put in the speed sensor, and also the system grows more complicated here, which means there needs more money and more attention, more maintenance stuff and all that stuff. It's more complicated compared to the open loop one here, which we don't need to measure the speed, and we just give it a frequency command. So again, it's your choice. If you know that your load does not change much and the load is almost constant, so that's fine, you can use the open loop and that will give you decent results. If you know that your load keeps changing all the time and you need your speed to be fixed with all the change in the load, okay, like for example when you're talking about an elevator system, like we said before, is we need to control the speed of elevator to be at a pattern. We want this pattern all the time, irrespective of how many passengers inside the elevator, because you know, yeah, If you just leave it like that, if there is one passenger in the elevator and it's a light load, that means your elevator will be much faster, and we don't like that. And if there is 10 passengers or maybe inside the elevator, that's a heavy load, and that means your elevator will be slower, and we don't like that. So for applications like that, while we need to just force the speed to be in certain value irrespective of the load, we go with this closed loop scheme, because it will just manage us to keep the speed at whatever the value we want irrespective of the load, because the actual speed is being just measured and fed back to your control system, and the control system updates its voltage and frequency to keep the speed at the desired value with all this change. Okay guys, so that's the basic idea of how can you actually control the speed of three-phase induction motor in open loop or in closed loop, and how actually the control is speaking to the power electronics converter by controlling the pulses going to the switches, and this power electronic converters, according to the voltage and frequency of these pulses, will generate a voltage with different voltage and frequency going to the actual motor to control its synchronous speed, and in turn it controls its mechanical speed. Okay guys, that's it. So that's all I want you actually to know about three-phase induction motor speed control. That is actually the most important stuff to have in mind. As I mentioned, always you will have more to learn. If you want to dig more about this, you will find much more details in your recommended textbook if you want to have a look at it, but I'm pretty satisfied with those actually of three-phase speed control of induction motor if you want to just stick with this. Okay. And this actually takes me to talk to you about a whole new topic, which is the starting of three-phase induction motors. Okay. So if you remember when we talked about the synchronous machine back, I told you I will talk to you again about the starting of synchronous motor once I start talking about the starting of three-phase induction motors, okay? Because they're just totally different aspects, the starting of synchronous motor and the starting of three-phase induction motor. And that's why I'm going to take you back to the synchronous motor again before I jump to talk about the starting of three-phase induction motor, okay? So bear with me and let's go back together to talk about the synchronous motors. Okay guys, so what about the synchronous motor? If you remember, we call the synchronous motor is not self-started motor. What I mean by that, the synchronous motor, again, just keep focused, I'm talking here about the synchronous motor, not our three-phase induction motor. Why? Because that is actually the best way to make you understand what I mean by starting of induction motor and what does this motor, okay? So the first thing comes in your mind when I told you that I'm trying to start the motor, that's the thing going back to the synchronous motor. Because the synchronous motor is not self-started motor. What I mean by not self-started motor, okay, that if you apply the three-phase voltage to the stator, the motor will not start rotating like the three-phase induction motor. The synchronous motor, you have also three-phase voltage, three-phase winding in the stator, but you apply three-phase voltage to it, it will refuse to start. The motor will not rotate, okay? Why? If you remember back when we talked about the construction, or how actually the three-phase or the synchronous motor works, if you remember that back, you have here in the stator, you have the winding, which is, yeah, so you have three-phase winding, that is A dash, and yeah, that is the other one, which is B dash, and that is the rest one, which is C dash. You have three-phase winding in the stator, and those guys produce you rotating poles, if you remember, that is maybe north, south, and those are just rotating around the circumference of the stator by the synchronous speed, 120 F/P, just like our three-phase induction motor. The difference is the rotor of the synchronous machine. If you remember the rotor of the synchronous machine, it has DC excitation to create its poles. So it has like that's a north pole here, and a north pole, a south pole, and a south pole. But those comes by DC excitation. That means they are not rotating by nature. If you remember, the rotating magnetic poles here comes only if you have three-phase winding fit from three-phase supply, like three-phase induction motor. But the rotor of the synchronous machine does not have this. The rotor of the synchronous machine is not three-phase winding. It's just one winding, a DC winding, yeah? And it's not fed by three-phase AC supply. It's fed by DC supply, okay? So the rotor of the synchronous motor is a single winding fed from DC supply, yeah? So its magnetic poles is not rotating like the ones of stator, okay? So what really happens is the poles of the stator, which are green here, are just rotating at a very high speed, which is the synchronous speed, 120 F/P, while the poles of the rotor are just fixed at the starting. They are zero speed. They are not rotating at all. And for the motor actually to work and develop torque, you have to have just a coupling between those poles. Each north pole of the stator is coupled by a south pole on the rotor and vice versa, and they rotate together. What's happening here is you have a very, very high speed vehicle, which is the poles of the stator, rotating at a very high speed, and another just passenger is just standing on the ground with no speed and tries to jump onto this car. It's impossible. So this what makes them cannot couple. You know what I mean? So what happens is the stator magnetic poles are rotating at the synchronous speed, 120 F/P, while rotor poles are stationary. They are not going anywhere. Okay, guys? That's why it is impossible for them to couple and rotate together. That is why it is not self-starting. That's what I'm saying. That's why this motor refuses to start from its own, because like you're seeing here, a big difference between the speed of the poles of the stator and the poles of the rotor, and actually they have to couple and rotate together for this motor to start rotating. Okay, guys? So that is why this synchronous motor requires an additional source, an additional method, additional something to be used to make it start. Okay? And that's what we'll be talking about. Fine. So that's why we call this, it's not self-starting, because it just refuses to start rotating from its own. Okay? We need to use the other method to make it actually rotate. How we use this? So that is why I'm just taking you back to this. So what we call starting of synchronous motor, that means the method used to make the speed of stator's magnetic poles and rotor magnetic poles close enough to couple and start rotating together to create torque and push the rotor body to rotate. That's what I mean by starting with synchronous motor. So if I asked you what I mean by starting with synchronous motor, you say that is the method I'm just implementing to close this gap, to make the stator poles and rotor poles are just running at closer speeds so they can pick up together, they can couple together and start rotating, and this will create a torque to make your rotor body rotate, and that's what you need from any kind of a motor. Okay, the most famously used methods of having the starting the synchronous motor, again, don't get confused, I'm now talking about starting of synchronous motor. I didn't talk about induction motor yet. So he has two very famous methods. Using squirrel cage in the rotor. Okay, what this means is you add a cage like the one used in three-phase induction motor in the rotor side by side with the DC excited rotor field winding, which is the regular winding of the synchronous motor. Okay, the cage is used to start the motor like the regular induction motor until speed of rotor is close enough to stator field speed, which is basically the synchronous speed. Then DC excitation is applied and rotor poles couples directly with stator poles. You got the idea? As for this, in the rotor of the synchronous motor, which is have the winding, it's fed from DC supply, we also use a squirrel cage like the one we use in the induction motor. Okay, they are there side by side, and you let this motor start like an induction motor. It will just be an induction motor actually, and it will start rotating. But you know, for the induction motor, the mechanical speed is a little bit less than the synchronous speed, not like the synchronous machine, while the mechanical speed exactly equals the synchronous speed, and that's why we call it actually synchronous machine, if you remember. So what's happening here is use this cage, put a cage inside the machine, and this will help you start like a regular induction machine, and your speed will be just a little bit below the synchronous speed. And where are you there? Apply your DC excitation, and now the speed is just a little bit behind, not this much gap that we had before. Okay, they are now pretty close to each other. So if you apply the DC excitation, they are close enough and they will couple together and start rotating together like a synchronous machine. Okay guys, so the first one is using a squirrel cage in the rotor and just start it like an induction motor. The other mean is using variable speed drives like the speed control we used before, just using power electronic converters. Okay, these are the variable speed drives used with three-phase induction motor, so you use rectifier and inverter to control frequency of stator. And this, like we used with three-phase induction motor before, the same idea. We use those rectifier and inverter to control the frequency of the stator. And this will control your synchronous speed, which is 120 F over P. You're controlling this frequency, and this will control your synchronous speed. And that means starting with low frequency, and that means low synchronous speed, low enough for stator and rotor poles to couple, and gradually increase speed to the rated speed. Got the idea? Rather than trying to speed up the rotor poles, now we are slowing down the stator poles. So that's a problem. You have stator poles with a very high speed and the rotor poles at a zero speed. So they will not catch up with this big difference in speed. So you have to do something. So the first one is using a square cage on the rotor, and this actually will speed up the rotor poles until they are just a little bit smaller than the stator pole speed. Or you don't use a square cage, but you use a rectifier and inverter, a variable speed drive, to control the frequency of the stator, and this will control the synchronous speed, which is the speed of the stator poles, and start with a very slow speed. So now the stator poles are very slow, and they can catch up with the rotor poles, which they are stationary. And once they are coupled together, we start gradually increasing the speed bit by bit, and now they will just start rotating together and catch up speed. Okay, guys? So those are the famous methods used with starting of the synchronous motor. Okay, guys? So when I'm asking you about what I mean by starting with starting with synchronous motors, or three-phase synchronous motor actually, is, like I said, those methods we are using to make the rotor of this machine start rotating, because it will not rotate on its own. Okay? And that's the whole thing I just needed to tell you about back the synchronous motor starting. But what about this, our own induction motor? Okay? And why this thing is a bit different. The whole thing is, now am I gonna just take you to talk about the starting of three-phase induction motors. Compared to the synchronous motor, the induction motor is a self-starting motor. What I mean is, just apply three-phase voltage to stator, and the rotor starts rotating on its own. Why? Because you know now, okay? Both stator and rotor have three-phase winding fed from three-phase AC voltage. Yeah? The stator one is fed from AC voltage from the supply directly, and the rotor gets its voltage by induction from the stator. You know that. Okay? And that means both the stator and rotor fields, okay, run at the synchronous speed from the beginning. So there is no difference in speed between them, and they can just couple together from the very beginning. Okay? The difference is that, if you remember, the synchronous machine, the magnetic field on the rotor comes by DC excitation, so it does not rotate on its own. So yeah, one of them is rotating and the other one is stationary. But for induction machine, both the winding in stator and the rotor are three-phase winding and have three-phase voltages. So both of them are rotating at the same synchronous speed. So they can actually couple together easily and will start rotating, and this will drag the rotor to rotate from the beginning. So it's a self-starting machine. It does not need all that headache we talked about before with the synchronous motor. Okay? So what does it mean by starting a three-phase induction motor? It's already started. It does not need any help to start. Actually, when I'm saying starting of induction motor, I mean the starting of three-phase induction motor is the methods used to reduce the starting current of three-phase induction motor. It's a whole different story. Your induction motor will not refuse to start. It will start on its own. But it has a different problem. It draws a very high amount of current at the starting, and we don't want this very high amount of current. We want to reduce it. So we use other methods to reduce this amount of very high current at the beginning. Okay, guys? And that's what we mean actually by starting of three-phase induction motor, which is totally different if you're talking about starting of synchronous motors. Okay, guys? So why actually the motor just draws a very high amount of current at the starting? Remember our equivalent circuit, okay? It is R1, JX1, and that is JXM, and that is your JX2, and here's our R2 over S, and that is V1, yeah? That is the current going into the stator, which we're more concerned about, because that is the current coming from the supply going to your machine. So the whole point is, this current, if you want to calculate it, it will be like V1 over the total impedance here. Okay, guys? If you're talking about running condition, the slip is a very, very small value. Remember, the slip is something like 0.02, 0.01, something like that. Okay? And this will make this R2 over S a very high value because its denominator, which is the slip, is a very, very small value. So being this is a very high resistance, like you see in here, that means the total impedance of the machine, Z total, will be high. And that means if we go back again to this method of how to calculate it, so if this Z total, which is the denominator of calculating the current, is very high, that means the stator current is low. I'm not laying low, it's just normal current. But that's all if you're talking about a running condition. But what's happening at the starting condition? At the starting condition, the slip equals 1 because the speed equals 0. Okay, guys? Unlike the slip equals 1, that means this R2 over S is now very small because basically the resistance is very small. The thing that makes this amount is high because the slip is typically very, very small, which is in the denominator. But here your denominator is just 1, so R2 over S is a very, very small value. And this in turn makes the total impedance of the machine a very small value, and this will give you a current as very high at the beginning. And that's why this machine is taking a very high amount of current at the starting. Okay? So the starting current of the machine is very, very high. And why we like this, why we don't like this, sorry, so the I starting is very high compared to I running. Okay? And what all the problems that comes with this problem? Okay? The problem is, you know that if you have very high amount of current, you will have two problems actually. Okay? The first one is this I starting when it's very high. That means the copper losses in your machine will go very high because you know the copper losses is 3I square R, yeah? So the current is very high, that means the copper loss is very high, and that means the efficiency of your machine will just drop down a little bit. Not a little bit, much actually, because your current will go high very much. Okay, but that's the thing that concerns your machine. And actually, if I'm good with it, I'm good with it. I'm fine. I want my machine to be less efficient. But there is another big problem that is totally not related to your machine. And that's why you have to mitigate this problem at once. That you're not having a machine out there in the desert, yeah? That's your induction machine, and that is actually connected to a bus. We call this in your power system studies a bus. That is the point you're connecting your machine to the grid actually. And what happens is usually this bus, which may be a substation out there somewhere in your public grid, you'll have other loads connected to the same bus because they'll not give you a substation just for your one motor in your factory, you know. There is other motor, maybe there's another motor here connected to the same bus. That is not our motor, that's another motor in another factory maybe. What will happen if your motor at starting draws a very high amount of current, so it will take so much amount of current from here. And this will drop the voltage of this bus down because there will be a very high amount of voltage drop here. You know what I mean? So your motor will have a starting current that's very high, and that means the voltage drop will be very high over those stuff, and that will make the voltage of the bus connected to it will instantly drop down because you have a very high voltage drop. That means this motor, the other motor that's connecting the same bus, will now have a very small voltage. Have a dip in the voltage connected to it. Okay? And that's something you cannot permit. Why? Because if you remember back to your torque speed characteristics, the torque equals 3v Thevenin square over R Thevenin plus R2 over S. Okay, squared plus x2 plus x Thevenin squared multiplied by R2 as by S of omega S. So if this voltage of the bus connected has just gone down, that means this Thevenin voltage goes down. And while the Thevenin voltage goes down, the torque of your motor goes down, remember? So the torque capability of this other motor will drop down so much. So if it has a heavy load connected to it, it maybe will not handle this load. Maybe the motor will be burned. But this is not permitted because all these devices will have a protection. So this protection of the other motor will actually trip the motor from the bus. See what is happening here? So your motor has taken a high amount of current at the beginning, may cause other motors connected to the same bus at other facilities to be forced to trip, forced to be disconnected because the voltage going to it is very small because your motor is taking a very high amount of current, which making a very high amount of voltage drop. Okay, so it may cause other motor connected to the same bus to trip by under voltage protection. So these motor have schemes to protect it against under voltages, and this will just trip those other motors and stop them from working, and that's something not good. So having a very high amount of starting current actually have a problem inside the machine itself by having higher copper losses and less efficiency, but also it has problems concerning other machines that connected to the same bus with you. So actually, if you don't want to do it for yourself, maybe the grid you're just connecting to will force you to reduce this starting current because there is other customers that needs not to be tripped because your motor is big enough to have a very high amount of current and make their voltage dips. Okay guys? And that's why we need to do something to reduce this very high amount of current at starting of three-phase induction motor. And that's why we are just more concerned to study the topic of starting a three-phase induction motor, which is actually the method we can carry out to reduce this very high amount of current that the motor draws at starting. And that will be our topic starting next lecture, to study the most commonly used method to reduce the starting current of three-phase induction motor. Okay, so thank you guys so much for joining me today. Take some time to review this and send me your questions if you have any, and yeah, see you next time.